Hello, welcome back. Today we will be looking at electrical forces and electric fields. For electrical forces, we're going to have a formula called Coulomb's law. What this tells us is the electric force between two charges that are separated by a distance. Now you may notice that it looks similar to the universal law of gravitation that we had earlier in the year. And just as a quick reminder, that formula looked like this: the gravitational constant times mass 1 times mass 2 divided by the distance squared. So when you get to the Quest and Kia assignments, you might be asked to compare and contrast these two forces. With a gravitational force, I don't know if you remember, but the gravitational constant was a really tiny number. It was on the order of 10 to the negative 11th. Well, with an electrical force in Coulomb's law, we have the constant of a K, so it's a capital K, and this is actually a large number. It's 9 times 10 to the positive 9th. And then for the gravitational force, we were comparing two masses. For the electric force, we're comparing two charges. So remember, on your subscripts, you can make those whatever you want. I just used 1s and 2s, but it's to distinguish that you have two different charges. And then both forces were divided by d squared. So what this means is the same thing as we had for that universal law of gravitation earlier. Our force will vary inversely with the square of the distance. So you are going to have some relationship questions asking you about how force and distance are affected when one of those two things changes. And then one other thing that makes the gravitational and electrical force different was, remember, masses can only be positive, so our gravitational force was always a positive number. Whereas for Coulomb's law, our two charges that we're multiplying together, they can be positive or negative, so that means our force will be positive or negative. We are going to have an attractive force if that value, once we calculate it, turns out to be a negative number, and that would be because we're multiplying a positive number times a negative number, and this would indicate opposite charges, and remember, opposite charges are going to attract. And then a repulsive force is going to be a positive number, and we can get that result by multiplying two positive charges together, or we can multiply two negative charges together. So if I multiply two positive numbers or two negative numbers, I'm still going to get a positive answer. And then that would also indicate that it's a repulsive force because we would have two like charges. So for our first example problem, you are given the average distance between a proton and an electron, and we're asked to find the electrical force between the two. So we would set up our formula, and then we can substitute our numbers in. The value for K is a constant. It's 9 times 10 to the 9th. And then for our charges, if you remember from your notes from last time, we wrote in and filled a data table in with the charges for a proton and an electron. So I'm going to use that data to plug in for my formula. So from that table, a proton had a positive 1.6 times 10 to the negative 19th coulombs, and an electron's charge was the same magnitude, but the opposite sign. And then we want to be sure to divide by the distance that was provided in the problem and then square that number. So take a moment and type that into your calculator and come back and check your answer. You should get an answer with an electric force of approximately negative 8.5 times 10 to the negative 8 newtons. Now, if you didn't get this number, you want to be really careful of your parentheses as you're typing in those values. This next example problem is a relationship type of question. So we've got two charges and they have a particular electrical force between them, and now we're asked to find if that distance between the two charges doubles, what happens to that force? So in this case, we can use coefficients and figure out how that force is going to change. Nothing happens to the K, so I can ignore it, and we're told that the only thing changing between my two charges is the distance. So if I were to look at how that new force is going to change, I would put in a 1 as a placeholder for each of my charges because they are going to be the same as they were before, but my distance is doubling. And notice that the distance gets squared in the formula, so I want to double that coefficient as well. So I end up with 1 over 4, and this tells me that the electric force, the new one, is now 1/4 as great as it was previously. So you've got a data table to fill out, so we're going to look at a couple of those same relationship type of questions. The first few are done for you, so this lets me know if I double one charge and keep the other one the same, that results in my force being twice as big. If I were to triple one charge and keep the other one the same, the force would be 3 times as big. Notice there's a direct relationship between the force and the charge. Now on this one, if I were to double one charge and triple the other, I would simply multiply the 2 times the 3, and that lets me know that my charge is 6 times as big as what it was before I changed those charges. And then we have half of a charge times one charge that remains the same, and that's going to cut my force into 1/2 of its original value. So let's look at these last two together. So if I were to make one of my charges half as big, I would put a 1/2 as a placeholder for that first Q. Remember the K is always going to be constant, so I can ignore that. So half of one charge, the second charge is going to double, and nothing happens to the distance, so I can just leave that as a 1 in the denominator. So to find out what my new force would be right here, I would simply multiply 1/2 times 2, and notice that those cancel each other out, and that leaves my force to be the same value as what it was before. Now for this example, remember nothing happens to the K, so I'm going to ignore that. One of my charges is cut in half. The next charge is quadrupled. And then nothing happened to the distance in that case, so I'm going to leave that as a 1. So I would multiply 1/2 times 4, and that gives me a charge, or a force, sorry, that is twice as big as what it was originally. Now let's look at this distance relationship. So remember that the force and the distance are inversely squared related. So the force is inversely related to 1 over the distance squared. So in this case, to show us how we got 1/4, that's the example problem we did in number 2. So let's skip to this one. Nothing is happening in the numerator, so the K doesn't change, the charges don't change, so I'm going to put 1s right there. But in this case, my distance is tripled. So I would put a 3 where the distance would go in the formula and square that. And that's where I end up with 1 times 1 is 1, and then 3 squared is 9. And that's how we got 1/9 of that force. So these next two are filled in for you. I'm going to go ahead and walk you through these at the bottom. So for this one, remember nothing is happening in the top. So I'm going to leave 1s as the placeholder for my charges since those aren't changing. My distance is quadrupled, so I'm going to put a 4 where the D goes in that formula and square that. And that's going to leave me with 1 in the numerator and 16 in the denominator. So that lets me know that my force is now 1/16 of its original value when I quadrupled that distance. And now we've got one more. So for this one, again, placeholders of 1, because nothing is happening to our charges, but our distance is 1/4 of its original value. So I put a 1/4 in where the D goes and then square that, and that's going to leave me a 1 in the numerator. And then in the denominator, when I square 1/4, that's going to leave me with 1/16. And I don't want a double fraction, so what I'm going to do is multiply by the reciprocal on the top and the bottom, so that I can cancel out that double fraction, and this gives me a factor of 16. So my force is 16 times as big of its original value. You'll notice on your KIA quiz, and we're going to take quizzes in class over Coulomb's law, you're going to have a lot of these relationship questions. And for our final slide today, we're going to look at electric fields. The definition is given to you first. It's the field that exists around any charged object. And it's also important to note that an electric field produces a force that can do work. So hopefully you remember the properties of force and work from last semester. The equation for electric field is a capital E is the symbol for electric field, and it is the force per unit charge, which means we're going to look at what that force is for every coulomb of charge. And then as far as our units go, force is measured in newtons and charge is measured in coulombs, so the electric field units will be newtons per coulomb. And then lastly, For electric field lines, you will be responsible for knowing how to draw electric field lines between like charges and between unlike charges. And you should have this website printed in your notes. I would make sure that I go through and look at the examples on that site because it contains explanations as well as some practice problems. So you might see those come up later on a quiz or a test, and it would be a really good idea to go ahead and take note of those and add those to your notes as well. That's it for today, and I'll see you next time.